All right, so in the last video, we talked about the difference between average velocity and instantaneous velocity. And instantaneous velocity started to build upon the idea that we might need a new tool. The new tool is going to be something we call the limit, where we take a quantity and send it very, very close to a given value. So in this video, we're going to define that term a little bit better. And we're begin with the formal definition of a limit, which, as it turns out, I'm going to write it here on the slide. This is not needed for AP. It's included in the back of your book. It's included in a lot of calculus books. This is not in the middle of section 1.1 because this book was written for AP coverage. But I'll read it just so you can kind of get a sense of what it means. Let C and L be real numbers. The function f has limit L as x approaches C if, given any positive number, this is called epsilon, there is a positive number delta, this is a lowercase delta now, such that for all x, the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus C is less than delta and x is not equal to C, we write this. So this is the first time the first time we have seen the idea of limit in its notation. So let's get into a definition of a limit that's going to work a lot better for us. So here's our definition. The sentence, the limit as x approaches C of f of x equals L is read exactly the way I just read it. The notation means we can force the function f of x, its y value, as close to L as we wish simply by restricting the distance between x and C, but not allowing x to equal C. Not allowing x to equal C. So that's a big point here. This limit does not mean x is equal to C, okay? Get that out of your minds. This means x gets very, very close to C. What happens to the y value of f of x? It goes to L. So the following examples we're going to see on the next screen show that it really doesn't matter if x is equal to C or not. The limit might be different things. So here's our definition continued with some examples. Take a look down here. There's a graph and a function of f of x is equal to x squared minus 1 over x minus 1. Let's take a look at it first. So this is the function f. And as x approaches 1, so as the x value approaches 1, what's happening to the y value? Well, the y value of this function, as we come from both the left and right sides, we are getting closer and closer to the y value of 2. Now, what happens at 1? Well, I bet you couldn't even figure it out if you only had pencil and paper, because when you plug 1 in, you get 1 squared minus 1 is 0 on top. You get 1 minus 1 is 0 on bottom, and that's, oh gosh, what is that? We haven't even gotten there yet. 0 over 0 is called the indeterminate form, so x equals 1 didn't do it. But the limit told us that this function approaches the value of 2. Let's take a look at function b, which is a piecewise function. X squared minus 1 over x minus 1. Hey, that was the function from before for all x's that are not 1. And then take on the value of 1 when x is equal to 1. So we see how that changed the graph of the function a little bit. So there was a hole in the graph, and it's been plugged kind of at the wrong spot here at 1. So again, as x gets closer and closer to 1, what happens? The y value seems to approach the exact same number, 2. So this limit would be equal to 2, even though g of 1 is 1. Just as we're pointing out here, g of 1 is not 2, but the limit is 2, just as it was in part A. And then finally, here's h of x, a new function x plus 1. This one has a point at 1, 2, and as x gets closer and closer to 1, the y value gets closer and closer to 2 again. So a bit of an idea here to kind of emphasize the point that the limit as x approaches, in this case it was 1, of some function f of x is not necessarily f of 1. Not necessarily do we just take that number and plug it in. We're talking about what happens to the function very, very close. So next up, some properties. This is going to help us expand the breadth of the types of functions we can take limits of. So first, some ground rules. If L, M, C, and K are real numbers, and the limit as x approaches c of f of x is equal to L, the limit as x approaches c of g of x is equal to M, then here's the first one, the sum rule. The limit as x approaches c of the first function plus the second is L plus M. Okay, that's pretty straightforward. Good. The difference rule works the same way. This would be the limit of f of x minus the limit of g of x. So that would be L minus M. Cool. Let's move on. The product rule works the same way. If we have two functions being multiplied inside our limit, those limits then are multiplied as the answer. The limit of the product of two functions is the product of their limits. Nice. Constant multiple rule. The limit as x approaches c for some k constant times our function is equal to some k constant times whatever that limit was that was known. So that's good again. And the quotient rule. The limit as x approaches c of a quotient of a function over another is again the quotient of their limits as long as that denominator is not 0. All right. So one more, the power rule basically says if you have the limit as x approaches some constant of a function raised to a power, as long as that power does not have a 0 on the denominator, then this is equal to the limit of that function raised to the same power. Now that was all very algebra language, lots of variables and letters standing in there for numbers and functions. So we are going to see pretty soon some real examples, and I think it's going to make a whole lot more sense. Some others to note. The limit as x approaches c of a constant is the constant, and the limit as x approaches c of x is the constant. So here's an example. Use any of those properties we just talked about to find the limit as x approaches c of 3x cubed plus 2x minus 9. The answer is given down below, but let's try this ourselves first. The limit as x approaches c of 3x squared plus 2x minus 9. So we're going to use a sum rule and we're going to use a difference rule and evaluate this then as the limit as x approaches c of 3x cubed plus the limit as x approaches c of 2x minus the limit as x approaches c of 9. All right, so we use sums and difference rules to separate this into 3 smaller problems. Next up, look at this first limit. There's a constant multiple. X cubed means x times x times x. So that's kind of sort of a product rule. So we've got a constant multiple. We've got a product rule. This is 3 times. What would be the limit as x approaches c of x? It'd be c times c because this is x to the third. So we're going to go c cubed plus the limit as x approaches c of 2 times x. 2 is a constant. The limit as x approaches c of x would be c minus the limit as x approaches c of 9, as we saw on the bottom of the last page, that's just 9. And so this cleaned up is 3c cubed plus 2c minus 9. And it looks a little bit nicer down below, but you can see we got the right answer. Actually, before we move on here, let's do another. How about if we wanted to find the limit as x approaches c of x to the 4th plus x squared minus 1 all over x squared plus 5. All right, well, first of all, this is a quotient of two functions. So one thing we can do is evaluate the limit as x approaches c of the top, the numerator, over the limit as x approaches c of the denominator. Then looks to me like we have a sum and a difference on top. We have a sum on bottom. So this is the limit as x approaches c of x to the fourth and of x squared and of 1. And it's the limit as x approaches c of x squared and of 5. And we can think of this either as the power rule or as a product rule, x times x times x times x. So that is going to give us a c to the fourth plus a c squared minus our limit of a constant is the constant, so that's 1. And then limit as x approaches c of x squared will be a c squared, and the limit of a constant is the constant, so that's 5. And we have an answer there. All right.